I'd go over at least some of the problems from the group work, which we tried today, okay, and get you started on this section. Part 1C. So we'll start here. F prime of x for c. You guys need to use the product rule, right? Let's make sure you did that correctly. So here's my u and v. So when I do u prime v, I get, well, 1 times e to the x squared plus uv prime, and I'm going to get an x, so plus x. Now when I do v prime here, what happens? It's e to the x squared, because the derivative of e to the x squared is e to the x squared, times what? I need to multiply by something because, dong, we have the chain rule. 2x, good. That's the derivative of that x squared. You guys with me? Okay, so final answer when I simplify might look like this. It might be e to the x squared plus 2x squared e to the x squared, right? Something like that. I've also seen it written this way sometimes. People will factor out that e to the x squared. See, what happens with these exponential functions is they kind of stick around a lot, because the derivative of e to the x squared is e to the x squared times something. And so people will put the leftover stuff here, you know, kind of factor out that exponential function. Yeah, that e to the x squared here, right? 2x squared, thank you. So that's how that goes. So then we were asking about number 2. And a lot of people did this. But you don't have to. There's another way to proceed I might mention. But a lot of people did this for part A. Okay? And if you do this, what I recommend we do is we try a substitution. Remember how I said let u be the thing in parentheses? What's the thing in parentheses, even though they aren't there? The 2x is the input of the exponential function. That's what I mean by in parentheses. It's really the input, right? So u is equal to 2x. So what does du equal? 2 dx. Do I have 2 dx? No, all I have is dx. And then there's this other step I showed you guys people sometimes do. What does dx actually equal then? 1/2 of du, right? And so you might begin this problem by rewriting it and saying, okay, this is the integral of e to the u times 1/2 du, right? Or 1/2 the integral of e to the u du. Because you can always bring constants out front of an integration sign. So what's the antiderivative of e to the u? Well, it's e to the u. If the derivative of e to the u is e to the u, then you can go backwards too. Plus c. And so my final answer would be 1/2 e to the 2x plus c. Guys see that? I'll show you one other way to do this, which sometimes comes up. Oh, did anyone do it differently? Yeah, Duncan?
Oh yeah, that's correct. I put u in for e to the x instead.
No, that's what I was going to suggest.
Okay.
Can we see?
Sure.
Cool.
Is this bulb going bad?
That must be. I'm going to call, I made it. So we're going to let u, same problem, let u equal e to the x. Try it. Write down what du would equal. That's easy. What's it equal? E to the x dx. I'm going to ask you the same question I usually do. Do I have an extra e to the x dx? I kind of do, right? Because if you take a look at the problem, I know it says e to the x squared, but wouldn't it be possible to write it this way? Right? That's what e to the x squared means, multiplied by itself. So if you look, what is this? That's my du. And so what I'm really integrating here is what? Be careful here. What am I integrating? E to the x is the same as u, right? So this is a different way to do the problem. And watch how it works. What's the antiderivative of u? When you integrate u du, what do you get? Not u. What do you get? I heard it. 1/2 u squared, right? This is a polynomial now, right? Think about it. What's the derivative of 1/2 u squared? It would be u. So I get 1/2 u squared plus c. Did that give me the right answer? So it's 1/2 e to the x squared plus c. And is that exactly the same as what I had over here? Yes. So I think that's really interesting to see, especially at the level you guys are at now, where you're still getting comfortable with making substitutions. You know, you can let u equal 2x and get the right answer, or you can let u equal e to the x and still get the right answer, as long as you do things carefully. All right, part B. What should I let u equal to do part B? Part B, we're going to let u equal x squared. Du equals 2x dx. Do I have 2x dx? No. Can I get 2x dx? Well, the answer here is no. You can't. Not possible. You can get it for part C. Do the same thing. And I'm going to try and explain why. You may not quite understand why yet, but maybe some of you do. Maybe some of you can explain. Why does C work, but B does not? You have the x and the dx, so I just need what? A 2. And how do I get the 2? I multiply by a half out front. So see, for part C, we're going to multiply by a half out front, and then we will have 2x dx, and then we'll just have this, well, e to the x squared right here. But the reason I did this stuff is because that pink, I'll just put the 1/2 out front, but that pink 2x dx, that's all going to become my du. And now, again, I remember what I did. The substitution was here. I let u equal x squared. So what is it that I have to integrate? E to the u. Okay? Again, the reason you can't do this in part B is because think about what you would have to multiply by. You'd have to multiply by 1 over 2x, but you can't do that. You can't bring a function out front of the integral without integrating. You're allowed to move a constant past the integral sign, but you're not allowed to move a function past the integral sign. Does that make sense? I see the difference? So, looking at this now, I'm ready to continue. And what's the antiderivative of e to the u? E to the u plus c. So final answer would be 1/2 e to the x squared plus c. So part B is not possible, but part C is. And yeah, I think the example I gave you in class at one point was e to the negative x squared. That's the bell curve. That's not possible either. Yeah, Garrett?
E to the u becomes e to the u again instead of e to the u squared.
Again, it all has to...
The derivative of e to the x is e to the x.
That's right.
Okay.
The derivative of e to the x is e to the x.
So it doesn't matter what letter it is, it applies the same no matter what.
That's right. I guess the real rule, Garrett asked a very good question here. We know this, derivative of e to the x is e to the x. But when you talk about this rule, what is the derivative of e to the u? If I write d dx e to the u, what would that be? E to the u times du dx, because u is some function of x. So you, just in general, you have to use the chain rule. Or I think the book writes it this way, e to the u times u prime of x. Okay. All right. Well, I guess we're almost ready for the back. But maybe not. All right, so I want to take the derivative of this, the log base 2 of x. We've never done this yet. The only logarithm we've taken the derivative so far is which log? The natural log. You guys know this formula? The derivative of natural log is 1 over x. I think you know that formula. That's not new. But what is new in today's section is this formula. The derivative of the log base b. Really what it is, it's 1 over x times what I like to call the fudge factor. You need to multiply by something. And the fudge factor for the natural log base b happens to be 1 over the natural log of b. And we'll show you why today. We'll show you why that is. But in terms of just learning formulas, that's one new formula. And the other new formula today is this, the derivative of b to the x. Right? What's the derivative of e to the x? E to the x. So what's the derivative of b to the x? It's b to the x times its fudge factor. What's the fudge factor of b to the x? Well, it's natural log of b. Okay? So, here I go. I'm going to do part A. F of x is the log base 2 of x. So what is f prime of x? F prime of x would be 1 over x times, yes, 1 over the natural log of 2, or you can write it as 1 over x ln 2. I'm directly applying the formula in pink above. That's all I'm doing. Okay? It's funny because if you don't care why, you could walk in, spend 5 minutes learning what the new formulas are, somehow memorize them, walk out and go do the homework. I mean, this is not that crazy, okay? Now, I'm not into magic. I want to show you mathematics. I mean, why would that be? Why is there a fudge factor? And I'll show you that today. But I thought for the group work, let's just see if you can just follow rules, right? I mean, that's really what's going on here. Part B, one of the things that makes it tough to follow the rules is knowing what these things even mean. This is a foreign language. I wrote x ln x, but what does that mean? First of all, how many functions are in part B? Just 2, right? X is one of them, and the other one is ln of x, right? So when I do f prime of x, once again, I need a product rule, right? This is my u and this is my v. So it's u prime v plus u v prime. Here we go. Where it says u prime, what are you going to write? 1. Where it says v, what do I want to write? Natural log of x plus, where it says u, I write x, and now where it says v prime, I write 1 over x. So this is a problem you could have had on last night's homework. Ln of x plus 1. There's part B. Okay. Part C, someone didn't like my little typo, so I'll try it again. F of x is x squared times 2 to the x. I've had this worksheet for a long time. The typo's been there. I just never fix it because I love the problem so much I don't want to get rid of it. So I just keep printing out the same worksheet and fixing it. All right. Same deal, guys. Let's do, this is my u and this is my v. Okay. And I'll pause and see if you guys can get it. Right here. Let's see. Let me work this out. F prime of x equals, so let's see if I do u prime v, let's see if you got that piece right, and then we'll do the uv prime. So u prime v, did you guys get 2x times 2 to the x, right? Plus, now u is x squared, v prime. That's where, the only thing new so far on this problem is I have to take the derivative of this exponential function, 2 to the x. And the derivative of 2 to the x, according to my formula, is 2 to the x times a constant. And that constant, that fudge factor, is what? Natural log of 2. Yeah. So there's my answer, I guess. What someone might do sometimes is they might factor out the 2 to the x. I've seen that happen, but I'm going to leave it like this. Okay, now let me ask you, have that question again, Calvin? Do you still have it? What was it?
No, I wrote down x to the x as 2x.
Okay, yeah.
That's why I wasn't seeing where we were using these rules.
Yeah, as a matter of fact, it's real important here to distinguish between, that's a polynomial. That's the old kind of function you had in chapter 1. Right, a parabola. And this is an exponential function. This is the new type of function we're studying in this chapter 7. So it's really important, I think. I think this example highlights those differences. Hopefully the whole worksheet does. Okay? So I want to go now and kind of give you guys a little run through on the why. And we'll do some more examples, okay? But why does it work? Bases other than E and applications. Basically, the formula in pink and the formula in green that I circled, we want to come up with what's the deal? Where are those coming from? Okay? So first I'm going to give you guys a definition. But I think I'm going to write B instead of A. This is an old slide. It's an old light bulb apparently too. So when I write, and this is section 7.3, when I write b to the x power, that's going to mean e to the x power times, right? So when I write b to the x power, what that means is e to the x power times the natural log of b. Okay? And the book says that this is a definition. And why are they saying that? Because first of all, I'm going to tell you that just yesterday I did this in college algebra. I gave them the same exact formula yesterday. I think it's our pre-calculus class, so we're trying to get them ready for this class. So I'm going to say that we already knew this. If x is a rational number. We already knew this. Why do I say that? Well,
Because you're putting you're bringing e to a power of natural log, and they're inverses.
e to the x and natural log of x are inverses. That's right. That's right. And what you really need here to see the equivalency is you need log laws. We know the log laws, right? So tell me what log law to use here. Well, the only logarithm's right there. So what would the log law allow me to do? See, this side is already b to the x, but this side, instead of writing x ln of b, that's right. We can take that x and we can slide it up here, right? That's the most powerful of the log laws. So then I get e to the ln of b to the x, right? And now here's what Mike was saying. E to the x and ln x are inverses, so you just get back b to the x, right? So I knew this. I knew that this was true if x is a rational number. What do I mean by that? A rational number?
It can be, yeah, it can be represented by it either terminates or repeats that.
Right, when you talk about decimal expansion, it terminates or repeats. But basically, the root word of rational is what? Ratio. What's ratio mean?
You get a ratio.
Fraction, right? So like, let me give you an example. Guys, if I say 8 and I say to the 2/3 power, does that make sense to you guys? What is 8 to the 2/3 power? No calculator, Tom. Because then you're not thinking. What does it mean? Okay, 4, but how? Explain, that's right.
You do 8 squared is 64, and then you cube root it, which is 4.
That's right. This is the power, and this is the root. So what Garrett did was this. He said, I'm going to do 8 squared, and then to the 1/3 power. And so the cube root of 64 is 4. I would have done it a different way. I would have done, sure, cube root of 8, and then square it. 2 squared is still 4. But we get the same answer. So it's well defined. This idea of any fraction exponent we have is defined. But now give me an irrational number, just so we have pi. What if I said 8 to the pi power? What does that mean? It means nothing until you got to this class. 8 to the pi power didn't mean a thing until you got to this class. Now it has a meaning. 8 to the pi now means, can we use this formula? E to the what? Pi times the natural log of 8. Now, does that make sense? I say yes, it does, because what's our domain of the exponential function? The domain of e to the x, we said, was negative infinity to what? So it's continuous. You could put any number you want, even irrational numbers, into e. Well, it's funny. Then we're going to talk about other bases. But until now, if I said take a number to the pi power, I had no idea what that meant. Now I do. If I say 8 to the pi power, what I really mean is the exponential function, which we define as the inverse of the log, to the pi times ln of 8. And since it's continuous and its domain is negative infinity to infinity, it's all well defined now. Okay? Which is good. Because we love these functions. Exponential functions are all over the place. Did I show you guys the calendar? I don't think I did recently. Here, let me go to your homework calendar. planned course schedule? Well, we could do that. It probably has it. So, yeah. No, this is wrong. This is all wrong. Let me find yours in a second here. Differentiate this one. This should be easy for you now. So, answer? What's the derivative of 3 to the x squared? It is 3 to the x squared times what? Actually, times two different things. Times two different things. So let me talk about why we have to multiply by two different things. Let's go back up to our definition up above. Okay? If I wanted to take the derivative with respect to x of b to the x, right? Well, that is the derivative of e to the x times ln of b, right? Because that's how I defined b to the x. It's actually you're taking the derivative of e to the something. But the derivative of e to the x is e to the x, right? So the derivative of e to the x ln b must be e to the x ln b times what? No? ln b. Why is it times ln b? Because of the chain rule. You could see it here. So what we did on the worksheet was, I wrote this down. The derivative of b to the x is, and we turned this back into a b to the x times ln b. That was the formula. Because this thing turns back into b to the x. Okay? So, when I want to do 3 to the x squared, one of the things I have to do is write down 3 to the x squared times the fudge factor. The fudge factor is the natural log of 3. All right? But then there's one more thing I need to multiply by in this problem. What is it, Garrett? Oh, I thought you had it. I need to multiply by the derivative of what's inside. So the derivative of x squared is 2x. So we get, there's the answer, right? Now, how would I actually write this? I don't know. I'd probably write it like this. X times 3 to the x squared times 2 ln 3. I think I'd probably write it like that. So I keep the constants together. Maybe, I don't know, something like that. We'll see how the back of the book writes it too, for problems when you do the homework. Let's try an integration problem. The problems in chapter 7 aren't new. You're either taking derivatives or taking antiderivatives, right? It's just the functions are more complicated. That's all. All right. Let's go with a hunch. What should I let u equal? Go ahead. Take a stab at it.
Square root.
That's what I would say. Square root of x. Let's see if it works. I don't know yet. All right? But I will try. If I let u equal square root of x, now write down what du equals and see if you have it. I'll pause while you guys work on this. So Tom did this, I saw. He wrote x to the 1/2. And so then du is 1/2 x to the negative 1/2 dx, right? maybe I'll rewrite the du as what? 1 over, since that's a negative exponent, that says put it in the radical. So does it make sense to you guys if I write it this way? See it? Right? So I want to make my substitution. Do I have what I need for my substitution? Yeah, you know, it's kind of funny. I need a 2 right next to the square root of x in the denominator. So I'm really multiplying by 1/2 on the inside, and so I'll multiply by 2 on the outside. See that? Then, so I have 2 times integral, and then what I have is I have 10 to the u, and then all that other stuff gives me my du. Do you guys see that or no? Okay. So now I'm ready to integrate, I guess. What's the antiderivative of, oh, do we have that formula? I guess the formula, see, I didn't tell you how to integrate an exponential function yet if it's not e to the x, right? But we can kind of deduce what it would be. If you have, because what's our formula we know? Let's go through it again. You guys, what is the derivative of 10 to the x? It's 10 to the x times what? ln of 10, okay? That's the fudge factor, right? So I hope that this makes sense to you, what I write down next. I'll bring my 2 down. And when I take the antiderivative of 10 to the u, I get 10 to the u times 1 over the natural log of 10. Why? Because I'm doing an antiderivative. So if I'm going backwards, I would divide, right, by 1 over ln of 10. Does that make sense? If you multiply by ln of 10 when you take the derivative, you're going to divide by ln 10 when you take the antiderivative. Because if I check my work, then the ln 10s will cancel. I'll get back where I started. So my final answer to this problem would be 2 over ln of 10 times, I guess, 10 to the square root of x plus c. Something like that. Okay. Again, what I'm about to do is one last definition, but maybe this is not quite the best way to do it. I kind of like what your book does better, so I want to go to your book. Here's exponential, logarithmic. So it's actually really nice. They give you kind of a study plan of how they do this. These 4 steps are the outline of these last 2 sections. It says, step 1, we defined ln of x, right? I did that this week with a picture. We integrated 1 over t, and it's this area function. And then, after we did a whole bunch of stuff with natural log, we got the exponential function. We defined it to be the inverse of the natural log. Now today what we did? Today we use the exponential function to define b to the x, these other bases. So what is b to the x? B to the x is e to the x ln b. Now, what I'm going to say is now that we have these new functions b to the x, let's compute their inverses. And the inverses we'll call log base b, just like you do in algebra. Okay? So we're going to have a family of inverse functions now, these log functions. So let's see where we do that. I guess right here. So the log functions. Okay. Remember, when you take an inverse, it's symmetric with respect to this line. Y equals x. And so this is kind of cool too. I can change the base. Actually, there's a better one below. Let me get it. Here. Ah, yeah, this is kind of nice. So here I have 4 to the x, and they're saying, look, guys, the slope right there is the natural log of 4. Or if I want a larger base, here's 5.61 to the x, and the slope at 0, 1. All these functions go through 0, 1. Even, why is this exponential decay instead of growth? Because why? The base is smaller than 1, right? So the base has to be some number between 0 and as big as you want, okay? Of course, the natural log, the natural choice, is base e. And there the slope would be the ln of e. What is the natural log of e? We define the natural log of e to be 1, okay? So the natural log of e is 1. Well, anyways, they start saying, hey, let's talk about the derivative. The derivative of e to the x is e to the x ln e by our new formula, right? Oh, but wait a minute, what's the natural log of e is 1. And that's why the derivative of e to the x is its own derivative, right? Here, let's change the base again. Let me go to about 4. There's 4 to the x. So the derivative is 4 to the x times the natural log of 4. You always have to multiply by the fudge factor unless e is your base. Then you don't need to multiply by anything because natural log of e is 1. So now what do I mean about logarithms? Logarithms are the inverses of those things. So like when I take some exponential function, I'll change the base again. Here it could be base 3, okay? So the log base 3 will be the inverse of that, right? Here's the log base b. Here's the log base 1.7. That's kind of interesting. If the logarithm can actually cross the exponential function if you have a really small base. Interesting. But in general, they kind of look like this. Okay? So that's the definition. And now, suppose you want to find a derivative. Because this is what your homework's going to be. Hey, here's a function. Compute the derivative. Here's a function. Find the slope of the tangent line. Here's a function. Integrate it. It's all the stuff you've been doing with new functions. That's the only thing we're doing differently in Chapter 7. In some ways, this is a great way for reviewing for your final exam, is study Chapter 7. Because you're doing everything over again with harder functions. If you could do them here, you could probably do them with just about anything. All right, here I go. So how do I take this derivative? F of x is the log base 2 of the square root of x squared plus 1. So f prime of x. I think I'm going to fit it here. Yeah, right. Well, we'll see. Now, I'm going to write it over again. I'll say over. Next page. Okay. F of x is the log base 2 of the square root of x squared plus 1. Is that what it is? Okay. So here I go. F prime of x equals. Now, I remember the derivative of logarithm is 1 over stuff times the fudge factor. What's my fudge factor? What's my fudge factor for this problem? So because it's a log, it's going to be 1 over the natural log of 2. 2 is the base I have. So this is what I need to multiply by. Okay? Exponential function, we did that on the last problem, right? The fudge factor was ln of 3 because the base was 3. But for a log problem, it's 1 over the base because that's the inverse function. Okay, so far I have 1 over x squared plus 1 times 1 over ln of 2 times, I need the derivative of what's inside. Does that make sense so far? Okay, but I've said I'm not done. Joey, question? Okay, so here I go. This is 1 over, why don't I just write this as ln of 2 times the square root of x squared plus 1 times, now when I go to find the derivative of this thing, remember, what are you thinking? Or maybe you even write it down. This is really x squared plus 1 to what power? To the 1/2 power. So here I go, bing, bing, bong. That other piece that I'm multiplying by is bing, bing. So this would be, well, I'm going too fast. So let me try it again. Okay, the other piece I'm multiplying by is bing 1/2, bing x squared plus 1 to the minus 1/2, and then bong 2x. Okay? But that pink stuff can be simplified. So let's do it. I have 1 over ln of 2 times the square root of x squared plus 1. That was the first pieces. And now from the chain rule, I got this. Can you see that the 2's are going to cancel? So you're going to get times x is in the numerator. The other stuff I put in the denominator. How come? You have a negative. So what goes in the denominator? Yep. So I need a square root though, right? Radical x squared plus 1. And so when you look at this, what does the derivative of the original function end up being? X over ln of 2 times x squared plus 1. That's right. Yeah, me too. I said I have to spread this out. Okay? So